Okay, hello, sir. We are from Group 6, and my name is Oh Sing Yang. My group member is Li Anqi, Tan Annie, and also Cecilia Chu Jing Chen. Today, we will present our final project OS, and our title is Penkel's Algorithms Deadlock Avoidance. Next, we will go to the introduction. The operating system is system software that manages hardware, software, resource, and provides service for programs. The main function of OS is resource management. It allocates CPU time, memory, and input-output device efficiently among processors. The deadlock is a condition where processors wait indefinitely for the resource held by others in a multi-programming environment. To ensure safe resource allocation and prevent deadlocks, the OS will use algorithms like Penkel's algorithm. Next, we will talk about the problem statement and objective. The problem statement is when multiple processes compete for limited system resource. It may lead to unsafe or deadlock state, so that the OS must decide whether granting a resource request keeps the system safe. And the objective is to simulate the Penkel's algorithm using C++. Second is to determine if the system is in a safe or unsafe state based on resource allocation. And third is to display the safe sequence of process execution if a safe state exists. And last is to understand how the OS avoids deadlock through dynamic checking. Next, I will pass to Anji.
For the design use, we start by entering the number of process and resource type. Then we input three metrics, which is allocation, maximum need, and available. This represents how many resources are currently used, what each process may need at most, and what resources are still available in the system. Then in the processing design, we first calculate the need matrix by subtracting allocation from max. Then we use the Banker safety algorithm to check whether the system is in a safe state. During the process, the work and finish arrays are updated dynamically as each process completes. Then for the output design, the program displays whether the system is safe or unsafe. If it is safe, it will also show the safe sequence of process execution. Okay. Next, for the algorithm use, first we input the number of process and resource. This set the size of the matrix we will use. Then we input three main metrics, the allocation matrix, the maximum need matrix, and the available vector. Then we calculate the need matrix using the formula need equals to max minus allocation. This tells us how many more resources each process still needs to finish its task. After that, we initialize two important data structure, work and finish. Work is set equals to the available vector representing the current available resource, and finish is set to false for all process, meaning none of them have complete yet. Next, now we search for a process I such that finish is false and need is less than or equal to work. This means we are looking for a process whose remaining needs can be satisfied with the currently available resource. If we find such a process, we simulate that it runs to completion. When the process finishes, it releases all its allocated resource back into the system. So we update work by adding the allocation of that process to it, set finish to true, and add the process to the safe sequence. This represents the order in which process can safely execute. Then repeat step 5 and 6 until all processes have finished or until no process can be found that satisfy the condition. Finally, when the loop ends, we check if all processes are marked as finished. If every process has completed successfully, the system is in a safe state. and we display the safe sequence. But if some process remain unfinished, it means the system is in an unsafe state, indicating that a deadlock could occur if resource requests continue. Next, I will pass to Cecilia.
First, for my part, I'll be using C++ to present the Banker algorithm. First, our program was require user to input the number of processes and resource type. Next, we got three important metrics. First is the allocation matrix. Second is maximum need matrix. Third is available resources. Then we need to calculate the need matrix. We apply the formula, which is need same with max minus allocation. Next, the here for the line 38 is the finish is used to mark which processes have completed execution. For the line 43, the works is used to keep track of available resource dynamically during simulation. And for our main loop, it used to check each unfinished process. If its need is less than and equal to available, the process is allowed to execute. After finishing, it is allocated resources. This continues until all processes finish. If not possible, the system is unsafe. Last is a user for output safe sequence. If all processes are finished successful, the system is safe and will print the safe sequence. Otherwise, it's unsafe sequence. For the test case, we got two test cases, which is using the 5 for the number of processes and 3 for the number of resources. And first, this is a safe state for the case that indicating deadlock, and second is a case that represents an unsafe state. It shows if it's stiffness in deadlock. Next, I pass to Annie.
Now let's look at the analysis. The first one is performance. The program correctly simulates the banker's algorithm to check for safe process execution. It used nested loop to find process whose resource need can be satisfied. Once a process finishes, its resources are released back into the system. The process continues until all process complete in a safe state or no further progress can be made, which means an unsafe state. The time complexity is approximately O n squared times n. And the second one is limitation. There is no input validation for incorrect or negative value. The program uses fixed size array, which limit flexibility with large or dynamic datasets. It focuses only on the safety algorithm and lacks the resource request feature. It also generates only one safe sequence, even though multiple may exist. And the last one is improvement. Input validation should be added to handle invalid or negative input. Using vectors or dynamic memory would provide greater flexibility. Implementing the resource request algorithm will make the simulation more complete. And the last is enhanced output formatting. Next. In conclusion, this project successfully demonstrates the banker's algorithm to prevent deadlocks by determining whether the system is in a safe or unsafe state based on resource allocation. It provides a clear understanding of how resource management and deadlock avoidance work in operating system. Although the program has some limitation, it effectively meets its objective. Future improvement could focus on aiding dynamic inputs, real-time features, and optimizing performance. Next. That's all for us. Thank you.